Well, I haven't started to project yet. Right? Because when I really start projecting, then I'll bring the house down here. Thank you for introducing me, and I'm kind of surprised myself that after 27 presentations, I still have something left to say, and even more surprised that there are people willing to listen to it. But thank you. It's an honor to be invited to address this club, and I hope that you'll enjoy what I want to share here. Tonight's topic is Dragonfly, as Bill said, and that's a mission to go explore Titan. Titan's been explored by some spacecraft, but it's time to go look a little harder and answer some of the questions that we learned to ask from the last round of Saturn and Titan exploration. There's a long list of people to thank in this one because it took lots of. I got resources from lots of places, starting with the principal investigator for the Dragonfly mission. It's run out of. It's a project of the Johns Hopkins University Applied Physics Laboratory, and Dr. Elizabeth Turtle is the boss for this particular project, and right beneath her is the name of Dr. Ralph Lorenz, who has actually written many books, including a few books about Titan and Saturn that were helpful. There's never a moment when Ralph isn't writing some paper about a new idea that's occurred to him, whether it has something to do with sand dunes or something to do with balloons or helicopters or airplanes or a new place where he could be applying his knowledge of spacecraft. Dr. Sarah Hurst of Johns Hopkins University is the university, not the APL, is a chemist who simulates planetary atmospheres in a chamber in her laboratory, and she is an expert on studying in the laboratory the processes that might that go on in the atmospheres of Titan or Pluto or Neptune, or name your favorite extrasolar planet, and she's working on that. Becca Sapan, who's the mission operation or deputy. No, she's the mission operations manager for Dragonfly. Gave me a presentation, and Dr. Shannon McKenzie, also of APL, gave another one. And I'd also like to thank Robin Hart, who's an artist whose work caught my eye, and I asked her if I could include a little bit of it in my presentation. She's currently the president of the International Association of Astronomical Artists, which is a fabulous group. If you love space art, you love someone to show you a picture of the cosmos, or imagined spacecraft that we haven't built yet, or what it would look like close up if you were standing next to a nebula. They're the folks who do that, and they've banded together. Anyway, you will also see images by various organizations that I have either lifted or gotten from somebody's slideshow. Let's give this another try here. I'm going to have a fight with this thing the whole time, right? But from NASA, from the European Space Agency, from, of course, Johns Hopkins University Applied Physics Lab, and also a few pictures sprinkled in from Jet Propulsion Laboratory and Caltech. Now, in this talk about a strange craft that we're sending to a distant moon, I got fascinated by how to build Dragonfly. And I love engineering and spacecraft design and spacecraft operations. And I know that for every talk, usually when I give a talk like this, I'm going to talk about the science that motivates us to send a mission somewhere. And so I would talk about Titan and the basics of that, and then the wrinkles in it in Titan science that lead to the questions the mission is answering. But I'm not going to do that tonight. I am, and I'll apologize for if I have given the science short shrift. The science is later on in the talk, because how to build this strange Whirlybird is too fascinating to me, and I'm going to tell you about that first. So I just have this slide that says Titan. It's yellow. It is a very large moon. It's bigger than the planet Mercury and smaller only than, among all the satellites in the solar system, it's smaller only than Ganymede. It's bigger than all the others. It has an atmosphere, a rather thick atmosphere, and that is unusual. It's a cold and dense atmosphere. It is tall in the sense that Titan's gravity is low, so there's a very tall pile of gas stretching up to much higher than our atmosphere extends from the Earth. It also is notably hazy, and when the Pioneer 11 or the Voyagers got to Saturn and took a look, everybody was kind of disappointed that instead of seeing the surface of Titan, we were seeing all nearly featureless orange clouds. A little later, they understood the colors better, and it's more yellow than orange. It's kind of like Kodak or maybe a Caterpillar bulldozer. It's about that color. One of the reasons that it's hazy is that there is a chemistry going on in Titan's atmosphere that's unique in the solar system, but it's possible for some hydrocarbons to be liquid on its surface, and as a consequence, it has lakes, it has rivers, and sometimes it has clouds. And as I said, it's been explored by spacecraft. Mostly, the Voyagers gave us our first really good look at this, and people said, let's send a spacecraft to orbit Saturn and study its satellites. And so Cassini was launched in the 1990s, and Cassini carried a European Space Agency probe called Higgins, which actually parachuted into the atmosphere of Titan and studied it right there in detail and made it to the surface and sent us back pictures of the surface. But that, and I got this, I found this swell picture from an amateur astronomer named Brian Martin that, like, there's Titan, little orange dot, and there's its shadow casting on Saturn, and I can't, this is a 16-inch Dobsonian picture. I couldn't resist. The determination was it's time to land on Titan once again. And for any world in the solar system, there's a bunch of science questions that scientists would like to get answered. So they're constantly putting together proposals to say, let's go to this asteroid, let's go back to Venus, and so forth. In the case of Titan, one could perhaps send a spacecraft that orbited Titan, because that hasn't been done yet, only a series of flybys. Or you could make a lander and then land on one spot on Titan and dig up some of the soil and study it, sort of like the Viking landers on Mars. You could imagine a rover, make something with wheels. And all of these things are speculated. In 2005, we got, as I said, somewhere, but the first landing on Titan was the Higgins, and here's a picture. It parachuted down. It was a probe sort of like this in size. It carried 6 instruments, and it told us lots about the atmosphere all the way down. And it got a look with cameras at what was underneath the haze, and it was a fantastic landscape. And it managed to survive the landing. So it gave us at least a little bit of further information about the surface. So what would the next mission you'd propose to resolve some more of our science questions? It's even, one of the options I left out was a boat, because I said we had lakes of liquid hydrocarbons, liquid methane. And, but another option is maybe flying around Titan. How would you do that? Again, engineers are versatile and curious, and they come up with all kinds of ideas. Because Titan has a cold, dense atmosphere, mostly nitrogen. It's cryogenic temperatures like 94 Kelvin or so. So way below 0 Fahrenheit or centigrade. A little higher than the boiling point of liquid oxygen, and way higher than the boiling point of liquid nitrogen in our pressure. So, but cold, thick air is ideal for flying machines to fly around in. So if you could figure out how to power it and keep your electronics warm, then you might make an airplane, or you might make a balloon. And the people have looked at this, and in the context of we need to write a proposal within a certain budget that NASA has said, you know, and you write the proposal and you bid on it, and you say, we think we should build this, we think we can do it within budget, and they turn you down because the Venus guys had a better proposal that year or something. But every time a group of scientists and engineers gathers to do this, the proposal they generate gives them a better idea of how one might design a mission, and they go back and they take their work and save it for next time. I'm showing a hot air balloon, or the French word is montgolfière, that was proposed a few years back, and Jason Barnes at the University of Idaho had a team that proposed within a set of tight budget constraints a drone airplane called Aviator, and it didn't get approved. So one of the possibilities, one might imagine, is a rotorcraft. And the story of this project started, and there's a little paragraph here where Jason Barnes, having come off having had his proposal for an airplane turned down, was having dinner with Ralph Laurenz, and the two of them cooked up a scheme for flying a helicopter. That is, or a rotorcraft, I guess. Technically, maybe not a helicopter. They realized that drones had gotten better and better over the last few decades, and we have seen improvements in controls, in understanding the aerodynamics of multi-rotor craft. And we have better sensors all the time. And so they decided that they ought to look at this. They got some engineers together and studied varying the size and the weight and the power budget and the range and so forth of a possible rotorcraft, and decided it could work. So it was time to get together the usual bunch of people and propose a Dragonfly. And Dragonfly is an 8-rotor Whirlybird with, well, and it looks like you see here, and it's on skids. It's got rotors sticking out, and where's my stick? Here it is. You see a cylinder here at the rear that contains a radioisotope thermoelectric generator, RTG, that powers the whole thing, and the waste heat from it also keeps things warm. Am my voice coming through? Yeah. And it's got pairs of rotors, 4 pairs of rotors sticking out from its sides, all designed. The rotors are not real large; they're about like this. And the idea is that all of this will somehow fit inside the spacecraft that's supposed to bring it there and come safely through the atmosphere. So it can only be a certain diameter. So it's about 12 feet long by 12 feet wide or so. It's the size of a small car. And I guess it's the weight of a pretty small car, not quite a ton. How do you do a mission like this? Well, some of the answers to these questions are standard, right? You need a cruise stage. You need a spacecraft that you could put on top of a rather heavy rocket and blast into interplanetary space, and it will keep your payload preserved and working until you get to Saturn. So this spacecraft will provide propulsion and guidance and communications, and the most of it is here, like propellant tanks and stuff. And because Dragonfly has a power source that can make electricity, and Dragonfly has a pretty good computer aboard it, the Dragonfly, deep inside here with no windows looking out, is hooked up to control the cruise stage. On top of the cruise stage, I already mentioned the reentry vehicle. It'll have a heat shield, it'll have parachutes, and it will, and the so-called back shell on top of the heat shield that protects protects the Dragonfly lander, and does the let's see, entry, descent, and landing, which is the space engineer jargon for coming down. When you see Mars landings, there's this, they talk sometimes about the 7 minutes of terror to get Curiosity landed on Mars. Starting from vacuum, your spacecraft screams through the atmosphere and gets really hot. And then at the right altitude, you pop the drogue chute, and that kind of stabilizes things. And after a while, you pop the main parachutes, and that slows it all down to a nice subsonic speed. Well, that process takes 7 minutes when you're entering the thin atmosphere of Mars. But on Titan, this process is going to take about 2 hours, because I said Titan's atmosphere is very tall. Okay, good. So you need a cruise stage, you need an aeroshell around your lander, and then you'll need a way of landing on the surface of Titan, right? So maybe you use airbags and it bounces to a safe landing. Maybe you'll use something weird like the sky crane that Curiosity and Perseverance used on Mars. Or maybe you won't do any of those things, because you've built the vehicle that can fly in the atmosphere of Titan, right? So the scheme for Dragonfly is to, sure, parachute in, but then drop the heat shield, and hanging, mounted in the back shell Dragonfly is just sitting there. Here's the view from above, from inside the back shell. The rig that's holding the lander up it extends some arms and is able to drop the lander, and we spin up the rotors, and it flies away from this thing and doesn't need the parachutes or the aeroshells anymore. But what was important, you don't need the weight of a landing platform or airbags or the sky crane stage. It just goes off and finds a landing spot and lands itself. I would think this is kind of a scary moment because the thing has never flown before. It is not able to lift itself by Earth gravity, so you better have tested everything you can test and simulated everything you can simulate, and be very, very confident that this will work on the morning that this arrives. But let's try it, because it's a great capability and it would save a lot of weight. So here's what happens on day one. Dragonfly departs from the aeroshell that delivered it. It has got a fully charged battery, because we've made sure that was the case before it reached Titan. And now Dragonfly's on its own, and it needs a landing site, and it doesn't have all that much time to find one. Maybe something like an hour worth of electricity for its motors. So it flies around the chosen landing spot on Titan and looks for the safest landing places, and it surveys a few places as it goes, and cameras and LiDAR, the laser equivalent of radar, feed it information to understand the landscape and decide where's a nice, safe, flat spot, or a flat, if not flat, then something with a very gentle slope that's not too steep. Find the best one. Maybe you already passed the best one and you went looking for more. You could fly back to the one that the computer decides is the best and make a landing on this nice, safe spot, your first landing on Titan. This is all, we're far away from Earth, so this can't be controlled by people on Earth. And everybody's just going to be waiting anxiously in control rooms for the signal from the lander about what it's been doing. But that is something you can test out on Earth. Can the software and sensor set for your autonomous drone really find find a good spot and evaluate it? You could try that out in Earth deserts, and that has been done. Okay, once you've landed, then Dragonfly has a high gain antenna that's kind of funny looking, but it's a hinge. It comes up on a hinge from the back, or I'll say the top of the drone, and it needs to swivel and point itself at the Earth. The Earth is in a fairly easy to find place, because from the vantage point of Saturn and Titan, when you look back to the inner solar system, the Earth is never more than about 6 degrees away from the sun. So you point the antenna pretty close to the sun, and you're going to be reaching the Earth. They do this in a more sophisticated way, but that's my quick way of explaining this. Now you've drained your battery, right? But you're sitting safely on the ground, and there is power from your nice warm radioisotope generator, and also a cooling system, or I guess a warming system, where liquid can flow throughout the lander from the RTG. So then during this time, on day one, and probably for many days beyond, you'll be checking out the systems and seeing how well everything works, and how all your gadgets, your instruments, and other functional parts of the lander like the Titan environment, and you have a commissioning phase. So let's think about the days to come. Titan goes around Saturn once every 16 days, and it also faces Saturn in the synced up way that our moon faces the Earth all the time. So Titan's day is the same as the period of its orbit, namely 16 days. This means that you will get 8 days of sunlight and 8 days of night. And if you'll recall what I just said, this means there are 8 days when the Earth is in the sky and your radio can talk to it, and 8 days when you can't possibly communicate with the Earth. And that kind of dictates your planning for how to operate. So let's say on some future day, oh, by the way, a day, just as on Mars, the Martian day is not the same length as the Earth day, so they call it a sol instead of a day. Well, the Titan day, being 16 times as long as an Earth day, is called a T-sol, and they will start be using that language in discussing operations. And here it's technically 15 days and 22 hours. Let's suppose that the sun is rising 1 T-sol, and Dragonfly's been working all night, and it's got a fully charged battery, doing perhaps a little science at nighttime, maybe not, but when the morning comes and we can see the Earth, it's time to downlink all the science data it's accumulated. So the antenna talks to Earth, and maybe this will be a T-sol where we go for a flight. So in the morning, maybe sort of 9 o'clock or so, as we'd expressed it on our clocks. After the sun's been up for a while, we'll go for a flight. About 1 hour of flying uses up about half of the battery capacity, so that'll probably be the typical duration of a longer flight. And of course, in the early part of the mission, they'll probably be going for much shorter flights as they cautiously test out the flight characteristics and so forth. But you go to wherever you're going, take a look around, go to your next landing site, or maybe return to the one you just visited, and then you have a lower battery, but it's time to do some science. Maybe you're drilling and collecting samples, maybe you're studying the nature of the ground or the weather or whatever, but there'll be some science activities for the rest of the daylight period. And when night falls, you might be doing some science, but for the most part, the battery will just quietly recharge and get all the way up to 100% ready for another flight. The red curve here is the elevation of the Earth in the sky. Early in the morning, it's pretty low, and as the sun and the Earth rise together, it gets up to a maximum elevation, and so these are the hours when you can be communicating with Earth as you get your job done. Sort of 192 hours in all, and then there's 192 hours of night. Now, you have been wondering, perhaps, when I was going to mention the Martian helicopter, Ingenuity, because we have indeed already operated a helicopter on another planet, and this was a big story around 2022 or so. I guess 2021 was the first flight. Ingenuity was a very small, very light, very low-cost device that was packaged along with the big, fancy, complicated Perseverance rover on Mars, and after some weeks after Perseverance landed, it unpackaged the Ingenuity, and Ingenuity was left on the surface of Mars with recharging its batteries with solar energy, and ready to begin making the flights. There was a small number of flights that it was designed for that were nominally the mission of Ingenuity, but it spectacularly did better. And instead of lasting for a few weeks and going for a few flights, it went several years and made 72 flights, ultimately covering 17 kilometers of distance. And after they tried it out and made sure that the helicopter was working right, let's see, in this picture, the yellow trace is where Ingenuity flew, and the white trace is where Perseverance crawled around the landscape. Ingenuity could just fly over some things that Perseverance had to go all the way around, but Ingenuity could fly ahead and kind of scout out the landscape to benefit the program of Perseverance's rover program, and this thing worked very well. And in the course of this, now the Ingenuity is not very much like Dragonfly, because the design of a helicopter for Titan is very different from the design that you'd use on Mars. However, they did learn something about how to conduct operations, exploration operations, with an aircraft like this, and sort of maximize the science and how to face some of the challenges and so forth. So Ingenuity experience is somewhat useful to the Dragonfly people. Dragonfly, as it goes around, will be finding its way by means of cameras, looking at features in the landscape and trying to turn that into maps and with elevations and such. As I said, it has a LiDAR, a laser ranging device that can measure the altitude of measure the height of the landscape, basically. So it'll tell you how high we are above the landscape, and that too can, with enough pings, can turn into a map. So there will be science cameras that are looking forward at where Dragonfly is going. There'll be science cameras looking downward to look at the landscape directly underneath. There is a camera that looks at microscopic views, so it can look very, very closely at the ground beneath Dragonfly's skids, and a couple of navigation cameras and such. Here's how you operate, or here's the plan anyway. Suppose you've landed and you're at a site that you know is a good, safe place to land. Then when you fly to your next site, you don't have to land there, actually. You can fly somewhere that you think might be interesting, and go look at a possible future site and gather a bunch of data, mapping data and other science data on a candidate landing site, and then you could fly back to the safe site, if you like, and land there and let everybody on Earth think about it until the next time, maybe a couple of weeks from now, when you're ready to make another flight. So that is the cadence for planning these things out. If Dragonfly has already surveyed a site and chosen someplace that they think is a pretty good landing site, then that could be the place it hops to next. After doing today's work and today's surveying, it might land might leave point A, go look at point C, and then come back to point B and land there and do a bunch of science there. This will be happening among sand dunes at first, the chosen landscape for the landing site. So there will be a dune here and a dune there, and the thing about dunes is there's flat spots in between dune 1 and dune 2, or maybe dune A and dune B. So maybe I'm just doing this. Tell me if this doesn't work, but I'm going to use this thing as a handheld microphone for a while. Yeah, and I just said everything on that was on this slide. Want to try? Yeah, sure. I guess. Do we have a? Yeah, it's on. Okay.
Yeah. Try that.
Yeah, let's do it this way. Yes, it keeps sliding off my head. Perhaps I use too much greasy kid stuff. The thing about having a lot of older members in your club is there's a bunch of people that understood that joke. Thank you. Now, we're encouraged that when somebody tells you for the first time about Dragonfly, and you see these swell pictures of this octocopter drone zipping over the landscape of Titan, you think, cool, we can fly around Titan and do all kinds of stuff. But the Dragonfly people kind of encourage us to think of this not as, something you can go on a joyride with, but rather a relocatable lander. It's actually going to it's going to be short flights of about an hour, and then sort of stay put for 16 days or something, maybe longer if they like the site they've reached. So and if there is more science to be done at that site. So actually, it's going to spend almost all of its time on the ground. And it is more like, imagine, let's see, like 1976, 50 years ago this summer, the Viking landers landed on Mars. And they were able to reach out and grab the soil and study it with various instruments and measure the Martian weather and take all kinds of pictures and so forth. But the people who were operating the Vikings found themselves, even though getting someone to buy you a lander that on Mars is a dream, they found themselves wishing they could see what's behind that rock over there, or maybe over that hill you can see in the distance. And they wished that Viking lander could move. And if you think of this thing, if Dragonfly can do that. Dragonfly is a laboratory stuffed with instruments, kind of like a Viking lander, but it can pick itself up and go to a different place. And so the notion that it's a lander most of the time, but it picks up and relocates itself every once in a while is a better way to think about Dragonfly operations. Now it can do some tricks because of all of the capabilities of this aircraft. It could hop. If you are in a place that you have just sampled and drilled into and so forth, but you'd like to investigate the neighborhood, Dragonfly doesn't have an arm that can reach over to a different spot in your neighborhood, but it can spin up the rotors and hop and fly over, even if it's just a meter or something, to a nearby spot and settle right back down in a very short flight, but reposition itself wherever you want the science to happen. And it can also shuffle. I'm not really sure what that is, what means. The articles said it can do shuffles. And I guess that's what, skidding along the ground or moving at a very low altitude somewhere around there. You can also use the rotor downwash as kind of a tool because, of course, the flow of air or nitrogen flowing through the rotors makes a wind that can blow up dust and sand at whatever material is on the surface, and you can see how much that moves. And because these folks have been, we've had space engineers turn themselves into experts on dunes and the geography of dunes and how they work. They've gotten really interested in what happens when a wind picks up a particle and goes and puts it somewhere else in a landscape, which is what people who study dunes study. You can you can get some science out of deliberately disturbing the particles on the surface. You can also use that wind to some extent to expose a lower layer of the dune you're on, and maybe return your scientific instruments to this lower spot and learn a little more. What they're really interested in, or let's say another thing that's sold as a big advantage, is that Dragonfly is going to land in a nice, safe field of dunes where they understand that there are flat parts from the data we have, but the rougher terrain around it hasn't been explored enough with enough resolution or enough data by previous spacecraft to understand where might be a safe place to land beyond the dunes. Well, Dragonfly can fly over the land beyond the dunes and then return to safe landing places and scout it out, further landing places, and gradually leapfrog its way beyond the edge of the dune field into an impact crater that they've chosen that's nearby and is interesting for a bunch of for reasons which we'll probably get to. And if we don't, remind me. But the real job of this mission is doing science on Titan, and this is the part I said I would shove to the rear of the talk, later in the talk. With some of the facts are laid out here. Titan is like 5,100 kilometers or so in diameter, and the gravity there is a little less than moon gravity on the surface. So it's 1/7 of the Earth's gravity, and the surface temperature, as I said, is also around 94 Kelvin. And here we have written the centigrade and Fahrenheit equivalents: minus 179 centigrade, minus 290 Fahrenheit. The everything around the solid surface of Titan is mostly made out of frozen water. But this frozen water is so cold that it's essentially as stiff as rock, as hard as rock. So on Titan, the air is nitrogen like our air, but the rocks are ice. The surface pressure is a little more, a little more than the Earth sea level pressure. We are about 1 bar in this room, and Titan's surface pressure is 1.5 bar, which is, as I say, not a lot more. It is about the same pressure you'd experience if you took if you dove into a lake and you were about 16 or 17 feet under the water. So you can survive that kind of pressure very nicely, and if you have a breathing apparatus, you can stay down there for as long as your air holds out and be perfectly comfortable. In fact, it's a rather shallow depth for as scuba divers consider it. And by the way, like most of the Titan talks I've encountered include this fact, so I'll tell you, but it's pretty science fictional. If you had a way to breathe, like maybe oxygen tanks and an oxygen mask, and if you had some way to keep yourself very warm, like the world's greatest snowsuit, and also if you had a pair of wings, then the atmosphere is so dense and the gravity is so light that you could actually fly under your own power by flapping the wing, flapping artificial wings. I don't know why. I don't know if you would ever really get to Titan and do this, but it's theoretically possible. Okay, and you know, if you're ever get a chance, maybe the tourist trade on Titan will someday be including flying yourself around the landscape with wings. Just keep your jacket zipped up. Atmosphere pressure, long days and long seasons lead to fairly calm conditions, and there aren't like big storm winds. There are winds of modest size, which is nice for designing equipment you want to operate on Titan, or aircraft you want to fly there. The diurnal, seasonal, and spatial change in temperature is about 1 Kelvin. Wow, that is like narrower than I would have thought. There's not so the weather doesn't change very much, much less than you'd think. And I already mentioned the tall atmosphere. We are between 8 and 11 astronomical units from Earth. So the light speed delay is about 70 minutes to 90 minutes as Titan and Saturn and Earth all go around the sun. So you are a long way from home, or there's a long delay between, let's say, us sending a signal to Dragonfly and Dragonfly responding back with some message about what's going on Titan. And it really has to do its operations pretty much on its own. In the atmosphere, I keep talking about nitrogen, but there is no oxygen to speak of in Titan's atmosphere, but about 5% of the atmosphere is methane, CH4. A hydrocarbon, or the simplest hydrocarbon, there are way below the 1/10 of a percent, or sorry, around the 1/10 of 1% level or lower. There's a few other species of gases, hydrogen and ethane and carbon monoxide, and there are traces of many other gases, many other hydrocarbons, and there are also solids in the atmosphere. I already mentioned that the rock, or the surface of Titan, is largely made of frozen water, but there are also solid particles of various hydrocarbons and maybe some other organic molecules that were created up in the atmosphere and fell from the sky, which I'll explain in a minute or two. And some of those things may have formed particles that are solid particles that are suspended in the air. That is where the haze comes from. Why the sunlight doesn't really get to the surface of Titan without bouncing around in a way that you can't see. When you look down on Titan, most wavelengths, you can't see much of the surface. You can see this haze. And when you look up from Titan, you probably can't see the stars or Saturn or any clear image of the. I imagine the sun is kind of a bright spot, like on a cloudy day, but that's about it. It is cold enough and high enough pressure that methane can be liquid or it can be vapor under Titan's conditions. So there is a whole cycle, like we have with water on the Earth, where it evaporates and then the vapor goes into the sky, but it reaches some place where it's somewhat colder, and the vapor turns into liquid, and it comes down as rain. It makes clouds, or it comes down as liquid water rain on Earth. Well, there'll be liquid methane rain on Titan. Not as abundant as it is on Earth, but in the colder regions, this happens a lot. It's also possible for ethane to condense. If there's ethane vapor in the atmosphere, condense and make a liquid. Ethane is not as likely to evaporate, so once it's on the surface, it probably stays on the surface. But this has the liquid methane with other hydrocarbons dissolved in it is what the lakes and the rivers and such are made of. Oh, and I also I found that here's Robin Hart's quilt. She made a quilt out of a map of the surface of Titan, and that is not a kind of art I've usually seen in planetary science. So I wanted to show it to you, and she's given me permission. Yay, fiber arts. Huh? Here is some of the processes that are going on to make Titan what it is. Way at the top of the atmosphere, say 600 kilometers or more above the surface, the sun is shining, so sunlight is coming down, and among this sunlight are some ultraviolet rays, right? Ultraviolet is pretty good at breaking chemical bonds for the kind of small molecules that make up Titan's atmosphere. So maybe the methane that happens to be there will a bond will break, and one of the hydrogens will wander off, and the CH3 ion will be left lonely, and we'll want to make some new friends. So maybe the hydrogen will find another hydrogen, maybe we'll find another carbon compound, but as they wander in the upper atmosphere, they bump into various molecules. Now, okay, ultraviolet could maybe break up an N2, a nitrogen molecule, and then you might have a loose nitrogen looking for companions. And so you can make out of this process carbon and nitrogen and hydrogen compounds in small amounts, but over the scale of a whole planet, it kind of adds up. And that is that's the genesis of larger molecules. And there's another thing that isn't in this diagram, but it turns out that there is a small amount of oxygen in the vicinity, which comes from, it turns out, this was a detective story, that the geysers of Enceladus are spewing liquid water and water particles and water vapor into the space around Enceladus and into the region of Saturn space, and ultraviolet and such break up these molecules, and so there are oxygen ions that sometimes come in from above, and so it's possible to make not only carbon compounds and hydrogen compounds and nitrogen compounds, but also compounds containing oxygen. Those are the four biggest molecules that we are concerned about when we think about life. So it became extremely intriguing to try to understand what's going on, what kind of chemicals get made up here in this process. What do they turn into when they start making, when all of these ions start making larger and larger molecules? Maybe they'll even make something like polycyclic aromatic hydrocarbons, PAHs, which there's like, I guess, so many of different kinds of them that they just lump them all in, and chemists usually lump them all into that acronym, PAH, but each one of these is its own molecule with its own characteristics, and you can think of those as perhaps little specks of black or brown stuff that are now floating around in the atmosphere. And if they start getting together into larger particles, you begin to have the kind of aerosols, the kind of floating particles that make up a haze, or something like a cloud, but really more of a haze is solid particles that scatter light and drift down, and they could eventually wind up on the surface. So the surface, which I said was mostly water ice, would be covered with some kind of distribution of hydrocarbon or maybe more complicated chemicals. Particles made of this stuff, which is, what stuff exactly? We don't know yet. We've modeled it, but it's time to go take a better look at with a drill at a more sophisticated chemical laboratory. So the big science questions are on this slide, starting with a quote from Carl Sagan about the molecules that have been raining down like manna from heaven for the last 4 billion years. And what intrigued him was that these molecules might still be there and not in the cold environment without a lot of active chemistry going on near the surface or in the lakes or whatever. They might be largely unaltered and deep frozen and waiting for chemists from Earth to investigate them. The Earth and the other planets started out without oxygen atmospheres, right? They started with a set of chemicals kind of like this, nitrogen and some hydrocarbons and whatever. And we cannot possibly study the early Earth because the Earth has changed hundreds of millions, if not billions of years ago, when oxygen started sweeping through and killing off whatever life had evolved without oxygen, and so forth. The Earth has radically changed in its chemical environment. Thank goodness, or we wouldn't be here. But it means that we have a hard time answering questions about how it was in the old days. Well, we have another place where, which is not quite like the Earth, and which certainly has undergone its own set of changes, but which is might have a lot of clues about the slow chemical evolution of stuff that doesn't involve an oxygen environment. And Titan is not exactly like the early Earth, but it can tell you a lot about environments like the early Earth. And that's what these other questions on this slide are. What makes a world habitable? Big question. We're always arguing, especially in the context of exoplanets these days. So let's get Dragonfly to investigate the cycle where methane evaporates and rains down and makes large bodies of liquid and so forth. And in those bodies, what kind of chemicals are mixing together or interacting dissolved in a methane lake, or happening in daylight on the shores of the methane lake, right? What chemical processes led to the development of life? Well, you're not going to watch that directly when you go to Titan, but Dragonfly can, can tell us something about all the complex carbon-containing compounds that I was just talking about, and this has an effect on our understanding of, quote, prebiotic chemistry in the solar system, a world that does not yet have life or might never evolve life, has got prebiotic chemistry, and we wonder if life has developed elsewhere in our solar system, and it probably hasn't developed on Titan, but Titan can tell you a great deal that points to some answers for that question. And they'll keep one eye out, but for quote biosignatures, but it's more like that Titan will fill in the background information. To get more specific, let's study the chemistry, figure out what chemical components are there, right? Especially for those interesting molecules that are biologically relevant, like the ones that might make up DNA and the ones that might make up proteins or be ingredients to a process that evolves those interesting molecules. What are the environments like on Titan, where we'd be interested in what's going on with the methane raining down and such. How does the geology of Titan move stuff around, and how does this says constrained processes that mix organics with past surface liquid water reservoirs. They're on a planet that cold. You're not going to have liquid water generally, but there might have once been places, or there might still be some places where liquid water could exist. And this sounds kind of crazy to me, but I understand this is a serious interest. When there's a big impact that, and an object makes it all the way through this thick atmosphere and survives to the surface and makes a crater in Titan, it's making a crater in the rocky surface, which isn't really rock, it's water, right? So it's put a lot of energy into a whole lot of frozen water, and for a moment anyway, or for one day, you get vaporized water and melted water, and you're throwing a whole lot of solid ejecta probably into the sky and making a splat, right? And we can see the scars of the crater. Well, I guess I've been told that it's in the aftermath of this collision, if it's big enough, the crater might have liquid water in it for a while, but it's very cold, and the water will freeze over. But if it freezes over from the top down, then there might be a reservoir of liquid water in this, crazy methane, hydrocarbons mix of an environment. There might be liquid water for a while, even perhaps for thousands of years for a big crater. That's nowhere near long enough for life to get started. But if we could find places where water and these other compounds mixed, then we might learn even more about prebiotic chemistry than if we were looking at an all hydrocarbon world. And so a crater is a big deal, or part of the landing site scheme, as we'll see in a minute. Let's see, it says here, search for biosignatures, make measurements. There's probably some real technical stuff lurking behind this. Like, what's a biosignature? How would you look for life? How would you be really sure that you had found it? And so forth. That devolves into big discussions of chemistry and geology and other environmental issues. So there's a set of technical questions that scientists would like to answer that would help with biosignatures, because biosignatures are a thing maybe in extrasolar planets we'd like to find. So if we understood Titan better, maybe we would understand that problem better. So what would you bring with you? That is, what kind of scientific payload would you load onto your Whirlybird in order to investigate some of these questions? I already mentioned cameras that can map the landscape and tell you a lot about what it's like, and throw in a microscope so you can look real close up at the grains of stuff on the surface. A drill to go with this, that is obtain samples, drill into the surface, and find out what's beneath it. Get yourself some samples of the stuff and feed it to an instrument that can do chemistry. Bring along a very fancy mass spectrometer descended from the one aboard the Perseverance, and it will help to answer a lot of these kinds of questions. Also bring along a gamma ray and neutron spectrometer so you can tell what elements, you can tell pretty quickly, without drilling into anything, what elements make up the stuff on the surface or immediately beneath it. And then bring along an array of sensors like a seismometer to see if there are any Titan quakes, or if you can understand the response of the surface to movements of like your drill. You of course want to know about wind and temperature and pressure and humidity, in the sense of, are the conditions right for liquid methane on or above or near the or beneath the surface, and electrical sensors, which on the skids, which can tell you something about the conductive properties of the surface between skids. Here's what these instruments look like when they're installed, or some general idea of where they are in the rover. The RTG is in the back, right? On the front, a lot of it is taken up by this red. Where is it? The mass. Oh, I guess this is actually orange. This is the mass spectrometer right here. The very fancy chemical laboratory packaged into a very small package. Suitable for spaceflight. The geophysics and meteorology package distributed in various places, with probes sticking out to measure stuff like atmospheric properties, and stuff on the skids to measure surface properties. That's all the yellow things. The gamma ray and neutron spectrometer is purple in this picture. The drill acquisition of, let's see, Draco, the drill for acquisition of complex organics. 2 drills are mounted on the skids, and there's a drill here and a drill here for redundancy, and a system of basically a vacuum cleaner, a way of pneumatically blowing particles that the drill digs up into the hopper of the chemistry lab. And let's see, I guess the other thing here is that the blue dots are cameras looking out in various directions. Now, this is a very busy slide that just gives a tiny flavor of what kind of data we might get back from Dragonfly. There's some pictures representing the various kinds of cameras looking at dunes on Earth, whether the forward cameras might see a big panorama of landscape you're about to fly over and so forth, and there are downward-looking cameras. I mentioned the microscopic things. Here's, I guess, some views of various substances as viewed by the microscopic cameras for Dragonfly. Over here, what kind of thing might the chemistry lab, the mass spectrometer, tell you? Well, it'll be a plot with little red dots on it, and it will be able to measure things that were in the stuff the drill dug up, and those things will have molecules of various weights. So there'll be a molecular weight plot, and there'll be these bars represent various processes that this lab can do on the sample, like heating it up and making vapor come off and so forth, to try to squeeze more information out of this stuff. And in this plot, there are bigger and bigger molecules on a log scale over here, and some diagrams of simple molecules here, but larger and larger molecules with benzene rings and stuff up here. This also represents a diagram of the gamma ray and neutron spectrometer, much like we've flown on other spacecraft, studying the surface by particular kinds of gamma rays that the elements in beneath the surface might give off. And here's some earthquakes, plots from a seismometer, which is going to be contributed by the Japanese Space Agency, to where if some kind of disturbance happens within Titan, then this instrument will produce traces like these, and the 2 traces here are the two plots are what happens if Titan has a very thick icy crust, and what happens if it has a somewhat less thick icy crust in layers below. And geophysicists can figure stuff like that out. Not going into this in any detail because I don't understand it, but again, that was to give you some flavor. So with the kind of data that I was describing, this spacecraft and its instruments could obtain, what kind of questions are going to be answered? And here, an even more granular set of questions, like what components, if you know what the components are in the environment, which of those, how would those chemicals drive processes of prebiotic chemistry? How does methane behave? What are the sources and sinks in the environment? And what can we learn about global methane transport from what we can learn from a little, a narrow neighborhood that Dragonfly will be able to explore? How are materials transported? Has liquid water been in contact with any of this material, especially organic material? And are there any chemical signatures of water-based life or even imaginary hydrocarbon-based life on Titan? Returning to a bit of engineering, and you could tell that this drawing was made by engineers because it says nothing about the scientific instruments. They're all listed as payload elements, and the parts that make the thing go and are concerned of engineering and operation are called out in here, like the LiDAR and the cameras and the rotors and so forth. But what I'm really interested in was I could find a drawing of a car and try to blow it up to be scale it up so it would be you could get a very close idea of Dragonfly's size there. It's about as long as a Mini Cooper within a few inches. Another good way to get an idea of the size is this wind tunnel test. There are lots of wind tunnel tests with lots of different, with a couple, 3 different configurations of Dragonfly. But I like this one because it is the size of the actual Dragonfly, except it's only half the size because it's only half a Dragonfly. And it is it is mounted here on the wall of the wind tunnel. They couldn't fit an entire one in here, and they could get all the data they needed for this test from half of an aircraft. So you see the rotors above and below, and the other rotors in the rear above and below, and you see them compared to the size of people, which is nice in this picture. If it's either a full-scale half Dragonfly or maybe a semi-octocopter. Did I put this in? Yes. It's my computer. I'm pretty sure this is an animation that will play. So I'm throwing an animation that shows all the bits and pieces on the chassis of the vehicle, and then encloses all of them in a box that's insulated to keep all of that stuff fairly warm operating temperature within Titan's frozen environment, and it acquires the external parts like the RTG housing and the main antenna and the rotors and motors. Here's I think that's the drill, and now you're beginning to see the outer shell with a few like aerodynamic instruments or meteorological instruments poking out here and there. There's another one in the rear down here. And it's acquiring a shiny cladding, so it doesn't radiate very much in the cold environment, and it will be shiny, and the shiny cladding will reflect the desert that it lands in on Titan. And so where are we going to go? That's a topic I haven't really covered. Here's a map of all of Titan, the best that Cassini, with its infrared and also some of its radar studies could show us. And I have some bad news. which is that most of the liquid and those exciting lakes and maybe rivers that feed them are up in the northern hemisphere, and we're flying. This mission was scheduled such that we're flying to Titan during the season when the northern hemisphere is having winter. So it's all of this is going to be pretty much in darkness for the length of the season, and a season is like 9 years. So in the 2030s, if you want to explore Titan, you really ought to go to the equator or the southern hemisphere. And that led to a choice that turns out to be a latitude not too different from the Higgins landing site, and also a longitude not too different from the Higgins landing site. So that allows us, the Higgins data is that about winds and weather is something that is very, very directly applicable to what are the conditions going to be like when we're flying this thing down on day one, and gave everybody some more confidence. There are the dunes I was talking about happen a lot around the equator, and there are a few lakes near the South Pole, but it's harder to reach that or it's actually kind of impossible. Well, that's the next slide. Right? So Dragonfly is going to land next to a crater near the equator. And the plan, when you're making a plan, if it's your job to pick out a landing site, you have to say, let's see, we're coming in from Earth on a direct trajectory. We can't go into orbit around Titan. This thing will enter the atmosphere and use the heat shield and pop the parachutes all directly, a direct entry on the first day. So that dictates that it's got to the landing site has got to be somewhere in here. If it this would be entering at a too steep angle, this donut hole in here, and outside this region would be too shallow. You want to land in the daytime so that maybe a considerable period, a few days perhaps before sunset, so that you can get your commissioning and checkout to happen in daylight, and that argues for being on this side of the Terminator, and that's kind of what led them to pick a target somewhere in here, so that the sun and the Earth would still be in the sky, and they could still communicate for some days after landing and during the checkout. And that led us to Selk Crater, which, as I said, is not far from the equator, and which is 80 kilometers in diameter. So it's definitely large enough to have some of that interesting water chemistry to have happened sometime in the distant past. Who knows how old this crater is? There aren't many craters on Titan, so probably the erosion of the surface happens enough that craters don't last for geological time. However old this is, and we might get a handle on that if we get some Dragonfly data. It has a nice set of nice, safe, boring dune terrain right south of the crater. And to blow up a piece of this picture, this is what the dunes look like to Cassini's radar, the synthetic aperture radar that mapped the surface. In this, we're not looking at a picture like with light would make. If you see a bright area here, it means kind of a rough surface. If you see a dark area, it's a surface that's smooth on the scale of the wavelengths of the radar, 2 or 3 centimeters. So the dunes have these nice dark areas that represent kind of smooth, not very reflective of radar, or sorry, not in the sense of a synthetic aperture image. And that turns into a prediction for gentle slopes, which are just what our aircraft needs when it wants to go touch down and begin its exploration. But tantalizingly, if your aircraft works out and you spend some months operating it and getting to know it, and you look around the dunes and land, and you do your chemistry on the stuff the dunes are made out of, eventually, maybe you can fly some tens of kilometers away and wind up on the fringes of the ejecta blanket of the crater. And if you're really ambitious, maybe explore upslope, find more and more good landing spots here and there as you go, and get closer to the center of the crater. And so that could be an exploration program to look at various kinds of terrain, possibly made of various stuff. Maybe in this ejecta, we can see material that was once in contact with water, and what chemicals might be in there that are different from the particles of the sand dunes. That's an interesting question, right? And who knows how far we could get. It depends on how many years the drone operates, and the range of safe landing spots that can be found. But it's an exciting prospect. Flying a lander or a relocatable lander over varied terrain is just what both the geologists and the chemists would like to see. So here's the landing ellipse southeast of the Selk crater, and here are some of the different kinds of materials that one might expect to encounter. The organic sand that makes up the particles of the dunes, and the materials in between the heights of the dunes, which might be somewhat different. I talked about the ejecta blanket, and if we got pretty close to the center of the crater, we could sample the impact melt and study that. So that is about all I have to say about Dragonfly for tonight. It's supposed to launch a couple years from now, so they're busy bending metal and furiously testing all the parts that have been manufactured and waiting for the next parts to be that have been manufactured to arrive and to be assembled. It has a long trip, so it won't arrive at Titan until 2034. But when it does, maybe you can invite me back for another talk to see what Dragonfly has found. When I was a kid, I was fascinated by a TV show called Whirlybirds, about people who, the wonder of the 1950s was the helicopter. You could do all kinds of stuff with helicopters, and if you were a helicopter pilot, you were really cool, okay? So in the spirit of that, here's a television show. The first half of it is an animation of what Dragonfly operation is going to look like, and the last half of it is the same rotating assembly diagram we've already seen. But here's Dragonfly has left the aeroshell and is striking out on its own and looking for a good spot to land and flying over the landscape and deciding to settle down, one hopes, and coming in for a gentle landing at a modest horizontal speed, and here we go. I said that the rotors might kick up some of the material on the surface, so I think we will see that in a second. Yeah, okay, the lidar and the cameras are looking at the surface, and here we are settling down, and there we are kicking up the dust on the surface and bouncing a little bit as we settle down in the 1/7 gravity, and when we're ready to stop, the rotors just stop. And erect the antenna on the top of Dragonfly and swivel it to point at Earth and start talking and saying, I'm okay, things worked, and once the initial science is done, take off and head for another site you've chosen. So that's it, and this is as I say, a rerun of the spinning thing. Now, like, Are there questions that I should be answering while this is playing? Yeah.
So the schematic listed the RTG as an MMRTG.
Oh,
It's
yes.
like a pretty big hunk of RTGs there. Is it one single RTG?
In this case, the what is it? Multi-modular RTG, MMRTG is the
They're usually smaller. 100
jargon.
megabytes.
No, this one is about the same size as you've seen on New Horizons or Perseverance and Curiosity run off one of these, and you could put more. The multi-modular is like you could put 2 or 3 of them together if you need a lot of power, like Cassini did, which it had 3 of these.
Bill, assuming this is going to launch in 2028, they must have already have gotten the plutonium-238 allocated, because it's in pretty short supply.
Yes, plutonium-238 is in short supply, and you definitely have to plan way in advance to get the stuff you need, and the Department of Energy and its technical people have to supply this module. But you know they know how to do that now, and anybody who's involved in our outer planets missions, whether it's a hot air balloon or an airplane or just a lander sitting on the surface, is going to need one of these. So all the engineers are fairly familiar with the steps one has to go through for this kind of probe to get the nuclear.
Repeat the questions as you take them.
Oh, I should have said, yeah. So that question was about the plutonium that is it's in the middle of the radioisotope thermoelectric generator whose gradual decay keeps the thing warm, and the heat that it gives off can be turned into electricity. Yeah.
So, 2 questions. The first one, if it loses a rotor, can it still fly?
If it loses a rotor, can it still fly? That is an excellent question, and that is the way that engineers think, right? And the answer is yes. If it loses one rotor, it can still fly. That's one of the reasons it has many rotors as it does. Or if it loses one of its motors, then the others can pick up the load. And that is again that kind of failure is the kind of thing you test with your Earth octocopter. I didn't show any pictures of that, but they've been flying a rig around deserts and whatnot on Earth, and you test. Okay, what if we switch off this motor?
Then you alluded to, most of the interesting compounds I think are going to be dissolved in liquid methane. If it stumbles across a large pool, which you can't see from images, does it have the ability to sample that liquid?
Does it have the ability to sample liquids? Not directly, no. It does. It can deal with moist soil that is, I guess, would be wetted by liquid methane. But it's also we're not really in a part of Titan that has liquid methane generally, as far as we know. Yeah, and it's also not there in a season or in a climate that is likely to produce much methane rain. And those are things you'd really like to study, and unfortunately, they're probably not going to be part of this mission. Although, again, everybody's aware of the possibilities, and they'll be looking out for some opportunity to find a wet environment and sample it. Yeah. Nope.
Is there any chance that it might end up flying through a rainstorm or end up being rained on?
Might it fly through a rainstorm or whatever? No, there's one. I mentioned that the weather is not very stormy, not very extreme on Titan generally. 2, they'll be constantly monitoring the meteorology, okay, with instruments, so they'll know if the conditions are suitable for rain, and hopefully get good at possibly predicting it. And I think that's something that they would rather not try flying through, especially since they don't have a way to sample the rain in the air. But if it rained somewhere nearby, then, or rained on the lander, then they would take advantage of the wet ground to take a look at that. Yeah.
I was just saying, like, I think, like, if they probably with their engineering, they'd probably make it a little waterproof as well, or something. Probably all this, probably there's somebody probably have to like seal it for dust and stuff. Might as well also make it waterproof.
Yes. The Huygens probe, in fact, was designed to survive landing in liquid because they had no idea what the surface was going to be like. So could it be solid? Could be liquid? Could be something mushy, and so forth. And the Huygens did not, in fact, wind up in a methane lake, but it gave us plenty of evidence of liquid methane in its pictures. So Dragonfly, as far as I know, is not expected to deal with bodies of liquid, and it's not going to a place where there are large bodies of liquid.
Like a little water resistant or something.
Yeah.
Like liquid resistant.
Yes, I'm sure that liquid wouldn't be a problem in the sense of surviving rain, or getting into a shallow puddle or something. But they would probably avoid any exploration of deep puddles, at least until they understood the surface of Titan a lot better, assuming they could find a puddle. I don't really know whether that's what the chance of that is, but yeah, Bill.
So the dunes seem to be in conflict with the fact that there's not a lot of wind. It seems like when you have dunes, you're going to have wind. So I don't get how those two things can
Yeah, I might have. You're saying I said there wasn't going to be much wind, but like dunes exist because of wind-blown particles. So how do I reconcile that? The answer is that I undersold the winds. That I probably should have said more. That there are winds. They're just not hurricanes. Okay, and they're modest winds. I think sort of like a maximum expected, maybe sort of 18 kilometers per hour or something. So there's enough wind to pick up particles and blow them around. But as far as we know, not gusts of really high winds, big storm winds, because there aren't any large temperature gradients that would drive that kind of atmosphere movement around the surface of Titan, as far as we know.
Quick question, what are the dates involved with this? Like, when are we expecting, has this already went? Are we expecting
No.
to learn more about it in the future?
They're building it. They've been building it studying it since the 2010s, getting it approved somewhere around 2018-ish or so, and sort of like 1,000 people are working to make this happen, and we are now at the stage where some of the components have been built and lots of testing is going on, and there are more components in the works. So over the next 2 years, this will all come together and get on top of a Falcon Heavy rocket and launch in 2028, it is hoped, arriving in 2034.
Okay.
Then we'd like some months of checkout, and then real science begins, probably like the end of 2034, beginning of 2035. Yes?
What will we use for navigating on the planet, on the moon, like an internal reference point, or external?
Yeah, what will they use for navigating? Because there's not a compass, or the maps they have are fairly crude, and they show details that are like hundreds of meters across or something. So we can't really, we don't have much to go on except the very grossest kind of detail. It's expected that the cameras and the LiDAR will survey the landscape and make decisions, build internal representations of maps of the terrain and make decisions about where to land on that basis. After day one, the landing, where Dragonfly has to decide all on its own where a good landing site is, it will get help from humans far away who will have enough time to consider the pictures, the LiDAR, and figure out like what they think would be a good landing site, either because it would be safer or because it would be more scientifically interesting, and give the lander suggestions. But again, it's going to operate autonomously. When it makes a flight, it's going to be operating out of the reach of Earth, so it will be under its own control. If that's all, I'll thank you again, and I appreciate being here.